Hi, in this video we are going to talk about the Klein-Gordon equation and the Klein-Gordon field in general. So the Klein-Gordon equation is given by this, where this box operator is known as the D'Alembert operator, and we are going to talk about this operator in detail later on in this video. But let's talk about this equation for a bit now. This equation is actually a relativistic wave equation, which is the quantized version of the usual relativistic energy momentum relation in special relativity, which is given by E square equals P square C square plus m naught square C raised to the power 4. And if you put P is equal to 0 in this equation, you put P is equal to 0, you get your usual E is equal to m naught C square, right? The famous equation E equals mc square, where m naught is the rest mass. M naught is the rest mass of the particle. Now, the solution to this Klein-Gordon equation is actually a pseudo-scalar field. A pseudo-scalar field whose quanta are the spinless particles, right? Whose quanta is a spinless particle, and the most common spinless particle we are aware of is, of course, Higgs boson, right? Now notice we are talking about a field, that is the Klein-Gordon field, and things change a bit compared to your usual classical mechanics, where you are used to, work with the generalized coordinates and the derivatives of those generalized coordinates in the Euler-Lagrange equation, which was just d by dt sum del L of del q dot minus del L of del q is equal to 0, where L was your usual Lagrangian, right? And q was your generalized coordinate. Here, a new concept of Lagrangian density is introduced, right? I'll denote the Lagrangian density with a curly L. This is your Lagrangian density, and the notion of Lagrangian is still there, but the Lagrangian now is defined as L equals the integral over the entire space, that is the volume integral of your Lagrangian density, right? This is the Lagrangian now. And then how do you obtain the usual action, right? The action is defined as, the action integral is defined as S equals the usual integral of your Lagrangian with respect to time. This is your action in the field theory, which is just given by the integral over the entire space and time of your Lagrangian density, right? And your Lagrangian density is just dependent upon, say, the field, its derivative, some x, some t, and so on, right? This is your action in the field theory. Now, you can apply the usual variational principle on your action, right? That you have learned in calculus of variations, and then you obtain the solution to this integral, which is again of course, the famous Euler-Lagrange equation. But things change a bit now. So now the Euler-Lagrange equation is given by this derivative d mu of the Lagrangian density with respect to the derivative of field minus the derivative of Lagrangian density with respect to the field. This is your Euler-Lagrange equation in field theory. Now, let us talk about this a bit. Phi is your field, of course. Now, whenever I write d mu with the mu in the subscript, this actually is a covariant index, right? This is a covariant index So d mu would just mean d by dx mu, right? This is the definition we are going to use for d mu, and whenever I use d mu with a, the superscript, this would be the contravariant index, and d mu would just mean this, right? So this is the definition we are going to use for both the covariant and contravariant index. So before we start writing down the Klein-Gordon Lagrangian density, you should be familiar with one more thing, that the metric tensor G mu nu is actually used to raise or lower the indices, right? So if we have say some rank 1 tensor given by I should write the covariant index like this. There is some rank 1 tensor which is given by a mu. Then notice that mu is the repeated index, and therefore it indicates that it is being summed over by the Einstein summation convention, and we would be left with a nu with nu in the superscript, right? So this is how metric tensor actually raises the index. And if we have say some a mu with a contravariant index, and we have some g mu nu, then this would result in the tensor with a covariant index. So here we have lowered the indices using the metric tensor, and here we have raised the indices with the metric tensor. Metric tensor is usually used in curved spacetime, but for the flat spacetime such as the Minkowski spacetime, we usually use a different notation known as eta, and the properties are pretty similar to the metric tensor, and it could be given by two different metric signatures, such as the metric signature could be something like plus, minus, minus and minus, or it could be something like minus, plus and plus, right? You can use either one of them, doesn't matter, right? So eta mu nu is a diagonal matrix with all the off diagonal components being 0, and of course the diagonal components being non-zero. We have all zeros over here and rest zeros over here, and you can notice that since it's a diagonal matrix, the diagonal elements actually represent their eigenvalues. So we have one positive eigenvalue and three negative eigenvalues. The positive eigenvalue actually denotes the direction in time, and the negative eigenvalue denotes the direction in space. So that's your usual special relativity thing we are familiar with. So coming back to the Klein-Gordon equation, the Lagrangian density for the Klein-Gordon equation is given by half eta mu nu, some d mu phi and some d nu phi, minus half m square phi square. Now you will note that this is not a very common form of the Klein-Gordon Lagrangian density which is written in the books. If you follow books like Peskin and Schroeder, the Lagrangian density is written somewhat different. So you can see that we can use this metric, operate it on this d mu, and this would result in raising the indices, right? So if we operate this on d nu, we are left with the Lagrangian density half d mu phi, and nu is the repeated index, and therefore it is getting summed over. So we will be left with d mu, but mu being the contravariant index, right? So we are left with d mu phi minus half m square phi square. Simplifying things a bit, this would be just equal to half d mu phi d mu phi minus m square phi square. This is the most common form of the Lagrangian density that you are going to encounter in the most famous books, right? We are going to use this form and proceed with our derivation. So the equations of motion for such a Lagrangian density would of course be given by the Euler-Lagrange equation, which would just be d mu dl by d mu phi minus dl by d phi is equal to 0. So you can see that mu is the index that is being used for the derivative and also in the Lagrangian density. So we are going to change things a bit, right? We would use a new index, say alpha, right? So we'll use the alpha index for the derivatives. So it would be d alpha dl by d alpha phi minus dl by d phi is equal to 0. So this is the form of Euler-Lagrange equation that we are going to use for our derivation of the equations of motion for Klein-Gordon Lagrangian. So first of all, notice that this part, right, m square phi square is the easiest part to solve, as it does not depend upon the derivative of the field, right? So now taking the derivatives, so working with this part first, we'll have dl by d phi equals to half d by d phi d mu phi and d mu phi minus m square phi square, right? Notice that we are taking derivative with respect to the field itself. So this part would be considered as a constant, and we are only concerned with this part, right? Minus m square phi square. So the derivative is ultimately going to be 1/2 minus 1/2 2 times m square phi, and the 2 is going to be cancelled, which would just be minus m square phi square. So we got our answer for the first part. dl by d phi is just going to be minus m square phi square. We should write it down and term this as equation 1. Now working with the second part, right? This is where the complication actually starts. We want to take the derivative of the Lagrangian density with something like this, right? This would just be d by d alpha phi of our Lagrangian density, which is d mu phi minus m square phi square. Notice we are taking the derivative with respect to the derivative of the field, and therefore this term is going to be 0, right? This is going to act as a constant. So our equation is simplified a bit. This is now d alpha phi of d mu phi. This is the only thing we are concerned with now, right? So here we will use our usual product rule. By the product rule, we are going to leave the first term, which is the covariant term, d mu phi, and we will proceed with our contravariant term, right? So that would be the derivative d of d alpha phi of d mu phi, plus now we will leave the second term, d mu phi, and we'll take the derivative of the first term, which is d mu phi, with mu as the covariant index. This part would be pretty easy to solve, right? Because you can see that we have a covariant index, which is d mu, and we are taking the derivative with respect to the covariant index. So this is a pretty straightforward thing. Let us see. Let us work with this part first. This is just going to be d mu phi d by d alpha phi d mu phi. Let us write down this equation in its actual form. It would be d mu phi of d by dx alpha phi, and we are taking the derivative of d by dx mu phi, right? Now this derivative can look terrifying at first, right? But this is not actually that complicated. Consider this to be some function. Let us consider this to be psi, right? Let's say that this is some psi. So what we are basically doing is that we are just taking the derivative of psi with respect to itself, which is just going to be 1, right? Nothing much to worry about over here. So this is something like that, right? This is just going to be d mu phi of dx alpha by dx mu. Now you would consider, why did alpha climb to the top and mu stayed at the bottom? Consider this to be something like when we used to work with the denominators of denominator, like we have some 1 by a by b, so b used to climb up, right, and a used to stay down. So this is something like that happening. I'm not an expert in this, but something like that is happening, right? Now let us take our focus to this equation. Now notice that this derivative that we are talking about is going to be 1 if alpha is equal to mu, and is going to be 0 if alpha is not equal to mu, right? And if you remember, this is exactly the definition of Kronecker delta. So what we have got here is nothing but the Kronecker delta. So this is going to be d mu phi and followed by the Kronecker delta. So we have essentially solved the first part of the equation, which is this one, right? We have solved this part. So now we should simplify things, and we should write down that it is equal to half times some d mu phi with derivative of d alpha phi and d mu phi plus d mu phi with the Kronecker delta. So we have simplified things a bit. Now notice what is going to happen if this Kronecker delta works on this d mu with mu in as the contravariant index. Let us see what is going to happen. We have a d mu phi and a Kronecker delta is acting on it, right? So let us write this in the actual form. This is just dx alpha dx mu, and we have d by dx mu phi, right? So this derivative, as we have already discussed, is going to be 1 if alpha is equal to mu, and it is going to be 0 if alpha is not equal to mu, right? So we have to change the index. It is only going to be 1 if alpha is equal to mu. So we have to change all the mu's to alpha. This is just going to be d by dx alpha of phi, which is d alpha phi, with alpha as the contravariant index. So the equation is simplified a bit further. It can be written as half d mu phi with the derivative d of d alpha phi d mu phi plus just this term, right? The equation got simplified further. Now we should deal with this part, right? This is a bit complicated. Why? Because we are taking the derivative of a contravariant term with respect to a covariant term, right? So what we can do is that we can use the metric to actually lower the indices, lower the index of this contravariant term and convert it into the covariant term, right? So we can use some metrics such as eta sigma mu, which could act on some d sigma, and notice that sigma is a repeated index and therefore it is being summed over, so we'll be left with some d mu, right? So now the equation becomes half times d mu phi, and we are taking the derivative with respect to some d alpha phi of eta sigma mu d sigma plus d alpha phi, right? This is the equation that we should work with now. Let us simplify this equation a bit further. This is going to be d mu phi by, let's bring this term over here to simplify it a bit. We have some eta sigma mu, and we are taking the derivative with respect to dx alpha, right? Dx alpha phi of some dx sigma phi, right? Plus d alpha phi. Now this is the same derivative we worked earlier with. So this derivative is just going to be d phi eta sigma mu, and this is going to be a Kronecker delta once again, right? This is going to be Kronecker delta with alpha at the top and sigma at the bottom plus d alpha phi. Now we can use this metric to actually raise the index mu and convert it to the contravariant form, right? So this equation can be written as some Kronecker delta and the usual Minkowski metric working on d mu phi plus d alpha phi, right? If this metric acts on this derivative, notice that mu is the repeated index which is being summed over, so you are left with sigma, right? So this equation becomes half times the Kronecker delta acting on d sigma phi with sigma as the contravariant index now plus d alpha phi. Now if we simplify things further, that is we should write the Kronecker delta in its actual form. It is going to be some dx alpha by dx sigma, which is acting on dx sigma plus d alpha phi, right? Now notice again that this derivative is going to be 1 if alpha is equal to sigma, and it is going to be 0 if alpha is not equal to sigma. So all we have to do is to change all the sigmas to alpha, right? So this will just change all the sigmas to alpha, and the equation takes this form, which is just equal to half times d alpha phi plus d alpha phi, which is going to be half times 2 d alpha phi, and it just becomes d alpha phi. So we come to the conclusion that dl by d alpha phi becomes d alpha phi, and if you remember the Euler-Lagrange equation, we also had to take the derivative with respect to d alpha of this whole thing, which just becomes this, right? So I'll mark this equation as equation number 2. And now if I should write down the equation first also. The equation first was just minus m square phi, right? And this was dl by d phi is equal to minus m square phi. This was equation 1. Now the Euler-Lagrange equation was just d alpha dl by d alpha phi minus dl by d phi is equal to 0. So if we combine equation 1 and 2, we end up with something like d alpha phi plus m square phi is equal to 0. Now there is one more thing to notice, that alpha is being summed over as it is the repeated index, and therefore it is also a dummy index. So we can replace all the alphas in this equation with something different. We'll use mu, right? So this just becomes m square phi is equal to 0. This is the Klein-Gordon equation, right? There are few more things to note over here. Now notice that d mu is just your Laplacian in 4D space-time, right? In 3 dimensions, the Laplacian was usually defined like this. This was in 3 dimensions, and in the four-dimensional space-time, this Laplacian is represented by the D'Alembert operator, which is defined to be 1 over c square d square dt square minus del square, right? So now if we use this notation for our Klein-Gordon equation, then the equation now transforms into something like this, right? This is our Klein-Gordon equation.